Hi everybody, my name is Benjamin Ige. I'm a software developer for the South African Radio Astronomy Observatory. Welcome back to our series of talks on radio interferometers. In this session, we are going to describe interferometric calibration. So, as with all physical instruments, there is sources of calibration error introduced by the system on our target signal. So this is what we are trying to get rid of during a process of calibration. So let's have a look at that. At this point, you should have gone through the mathematical background section already. This includes especially the Fourier transform and all its properties. And then also, you should also know what we mean by visibility. So this term, what we colloquially refer to is just a spatial coherency measurement that we capture with a radio interferometer. So yeah. All right, let's get started on this. Now, there's a bit of mathematics that we need to go through first before we can actually describe how we practically calibrate the instrument. We need to look at what is known as Jones calculus and how it relates the input signal to the measured signal with calibration errors. All right, let's recap what we mean by interferometer. Now, an interferometer is a system where we have two input antennas. These can be very simple measuring devices, such as like two little dipoles that you put on the ground that's separated by some distance indicated by the baseline vector there, B vector. Now, an interferometer measures the induced power stemming from a source out in the far field, right? By the time that the emitted signal, whether it's from a thermal process such as a black body or from synchrotron emission or Bremsschlang emission, gets to us, the measured signal will be a planar wave, right? So the interferometer measures both the power of that emitting source and the delay between an orthogonal direction of our baseline vector to the source, right? So we get a sense of where the source is. So as we say, this is just a geometric delay between the signal hitting, let's say, antenna P and another antenna Q, separated by this distance. The interferometer is maximally sensitive in a directional orthogonal to a baseline for instantaneous measurement, right? Typically, so what we're measuring here then is now the distance of the source of this orthogonal direction as it's projected, so the dot product onto our baseline vector. This is a cosine, if you recall your calculus from university. The cosine interferometer then is going to be maximally sensitive just in at the peaks of this cosine term. This introduces an artificial baseline length fringe pattern across the sky, right? As we've already seen in the talk about the visibility space. We also need the odd sine components if you want to be able to reconstruct the signal and to also make the interferometer itself sensitive to larger areas of sky where the cosine component will be in a null. So we also induce a 90-degree offset in the signal between antennas P and Q and take a measurement of that. So you can see this just illustrated at the bottom there. So you have this 90-degree phase delay between the two signals. So now we have so the interferometer now has a measurement of both the intensity and the cosine and the sine of the delay. The interferometer is sensitive to the mean of the sky only when the two antennas are right on top of each other. So if there's no distance between the antennas, so if you have like a single dish, that gives us a mean measurement of the sky. All the rest of the spacings are just differences of the mean. Typically, if you correlate now antenna with itself to get that single dish measurement, you get a correlation of noise with the same noise. So we typically throw that away, and therefore our interferometer is insensitive to the average flux density of the sky. Now let's look at what the interferometer measures. Now, if we look at a single antenna, the antenna measures an induced voltage coming from a propagated signal that is a transverse wave. So that transverse wave has a magnetic and an electric component to it. We're measuring the voltage of the electric component of the signal. The electric component, as it propagates through space, each component along the plane of propagation has a certain polarization component attached to it. So if you have an unpolarized signal, it just means that you have a signal that has equal power in one direction and the other direction. We can fully describe this propagating signal by just two orthogonal bases. So but let's say a horizontal and a vertical basis, or a left and right circular basis. Now let's take a look at the various different ways the signal can be propagating. The most generic form of describing the propagation with time of each of these points on the propagating wavefront is an ellipse, right? We have various special cases here. So if you look to the animation on the right-hand side there, the signal can be circularly polarized, right? So in that case, the Y component is slightly delayed or in advance of the X component of the signal, right? It can be linearly polarized as well, so it can be either horizontally or vertically polarized, right? So in that case, the ellipse is in this three-dimensional space is just either a line or a circle. So those are the special cases that we have in the middle there. So you have a vertical, horizontal or a vertical signal. You can have a 45-degree angle of polarization as well, so what we call Stokes U. Or you could have a circular polarization. And let's take a look at the illustration of these various modes. Well, we can capture the full polarization of this propagating signal by two angles, right? Firstly, the angle, like a horizontal and vertical angle in the XY plane, and another angle that describes by how much the signal in one of the bases is delayed with respect to the other. So that describes how circular the polarization is, so how much Stokes V you're measuring. So this is indicated on the point sphere there. So within the horizontal plane, you have left and you have horizontal and vertical polarization on the on the x-axis there. On the y-axis, you have a minus 45 or plus 45 degree polarized signal, and then, as I said, the other angle takes you towards a circular polarization, where you have a physical delay between the two measuring bases. If you take a snapshot look at a single plane in this three-dimensional space, right? So that is describing the signal that we're trying to measure. So this can be indicated as just intensity, I of x, I of y, in these two bases, whichever basis you select. So let's say nominally aligned vertical and horizontal bases, and a phase angle that describes the temporal variation as the signal propagates through free space. That is the signal that's unaffected by any calibration errors that is induced by either the environment or the system. Now, of course, in the first order, our system is going to introduce a lot of errors in this measurement. So Robert Jones, who worked for the Polaroid company in his early career, is a US-based mathematician who invented a calculus which we now name after him, so Jones calculus. And this calculus essentially tells us how to combine different systematic effects together to describe the measured signal that we have captured. So all linear effects induced on the propagating signal can be captured by a 2x2 matrix. The special case here is that the effects are non-depolarizing, right? So the total intensity remains the same. So the terms within these 2x2 matrices that describe all the effects on the propagation of the signal, so is complex valued. So as you can see, A, B, C, D are all complex valued parameters, and that matrix can be decomposed into several different matrices, so each describing a different effect. So the effect closest to the propagating signal is marked J1, and the effect furthest away from the propagating signal, so closest to our final measurement, is Jn. If you multiply all these different complex 2x2 matrices together, you get this final matrix. Now, these are all just describing linear transformations on the signal, and we calibrate them one by one, starting from the effect that is closest to the measured signal. Okay, so let's look at some examples of such 2x2 polarizers. Well, on the left-hand side there, we have a complex gain matrix, right? This describes both attenuation on the signal, right? And it describes impedance effects on the signal, so a delay or a constant phase change with frequency, or that may be variable in time, for instance, and so forth. Then we have in the middle there, we have a off-axis term that describes the non-orthogonality of our basis vectors. So if we have two physical dipoles, they might be slightly misaligned. So the horizontal dipole might be capturing some signal that only really belongs in the y dipole. So this describes this slight non-orthogonality of the signal. Typically, we would have substantially less non-orthogonality than we have calibration errors stemming from a diagonal gain term, for instance. So this will be on the order of about % level for Meerkat. Now the last term here is very important. That is a phasor matrix. It has no amplitude attached to it, so it's normalized in amplitude, but it has phase information attached. Now, this can take many forms. So this is essentially a special case of a gain matrix that just has this phase. The phase can be frequency dependent. If it's a slope in frequency, it means it's a delay, right? Or it can be constant in frequency, so that brings us back to a normal gain matrix with amplitude unity. The phasor can also describe the geometric delay between the signal hitting antenna P and antenna Q, for instance, and can fully describe this delay that we actually measure with the interferometer that we know. Other effects that we have to solve for during the calibration process is things like cable delay, where there is, you can think of an old analog system where you have a coaxial cable connecting the two antennas. There's a bit of kinks in the cable connecting to one that will induce a impedance on the measured signal with respect to the other antenna. It's important to remove that if you want to correlate those two signals together. So that is one place where we use a phasor matrix, for instance, and then ionospheric effects, of course, also can be described as effects introducing a delay in phase for various directions of the sky. Special note here that these matrices don't generally commute. So if you have diagonal matrices, so gain matrices, they can commute amongst themselves. The off-diagonal matrices and 2x2 matrices can't commute. And then constant matrices can, of course, commute with anything. So if you have a diagonal matrix where both values are the same, they can commute anywhere. So the order in which we solve for these terms are quite important. All right, so let's look at the measurement product. Now, as we say, that we can fully describe all the linear effects that might be introduced on this signal that we're trying to measure by a series of Jones matrices. If we look at a correlated signal, so if we correlate a signal between antenna P and antenna Q, it essentially just means we're taking a short-term average of the correlation product between those two measured signals. At this point, they already have some form of calibration error attached to them. What we're assuming in calibration is that our integration intervals is short enough for us to move these terms outside of the averaging interval, so they're relatively constant within the integration interval. And what we end up having is just a Jones term associated with antenna P, another Jones term JQ associated with antenna Q for all such pairs of antennas, and then we take just an average of these two signals. So let's look at a physical system where there can be many different effects on our signal. So let's bring this back into reality. Now, let's look at the meerkat system. The meerkat system consists of 64 offset Gregorian dishes. Each dish has an indexer platform with spaces for 4 receivers. Currently, there's a UHF receiver, L-band receiver, and S-band receiver system. The S-band receiver system is currently being commissioned. Now, within that, each of those receiver systems, we have the receiver itself. Right next to it is a digitization system. And all of that gets connected to our signal processor by fiber optic. So on the right-hand side there is the science data processor. The science data processor takes the time measured signal, it channelizes it. So these F engines, as they refer to, is the channelizing components. So it takes the time the voltage, the time variable voltage, it Fourier transforms that into the frequency space. So we measure in frequency in hertz, and it then takes the output from each of these F engines and correlates that together. So that is referred to as a FX correlator. You can also do the reverse, although it's much more processing intensive, because if you remember your Fourier theory, a correlation in one space is a multiplication in the other space. So this is why we typically do the channelization first. All right. Part of this system has a time reference system which sends out signals to our antennas, to the digitizers on our antennas, so that we can timestamp the signal between the different antennas for the purposes of correlation. Now, let's look at right at the front end there. Well, each of these meerkat receivers will have a horn, and a waveguide. At the end of the waveguide, there is a dipole, right? So vertical and horizontal dipole. And at the back of that, within a temperature stabilized enclosure that's cryogenically cooled to about 22 Kelvin, we have the low noise amplifier, which is a two-stage amplification system. That system is now connected to our digitizer, which is sitting right next to the receiver. Within the receiver, there's a analog to digital conversion system, and at that point we timestamp the signal and we send it through to our signal processor. The system effects that can be introduced at this point is, well, the following. Let's start right closest to the purest form of the signal here. The antenna has a far field response. So remember, meerkat is offset Gregorian dishes that are highly directional. Right? So the antenna itself has a attenuation pattern that can be represented by a full 2x2 term for all different positions on the sky. So it's a direction dependent effect. And then since we're on a alt-as mount, the sky rotates along a third axis. So where we're pointing our dishes, it will rotate with as a function of parallax angle, which is time dependent. So this beam will seem to rotate over the sky as we observe for a long time. The next effect here is just the delay term between the vertical and the horizontal dipoles. This will induce essentially circular polarization, right? Because remember, circular polarization is really defined as the delay between the signal passing through a dipole, let's say the Y dipole and the X dipole. Then we have maybe a bit of delay, further delay between that and the digitization system. There can be all sorts of systematic effects which adds further delay onto that signal and moves the X hand and the Y hand apart from each other. Then once the signal is digitized, we can have a delay between the signals, so a cable delay. That is this K term, which is a phasor, as we discussed, and a constant offset as well in phase, which is just can be described as a gain matrix, so G term. These are temporally variable effects that are affected by temperature variance and so forth. Within the receiver itself, the bit of cable that actually attaches the digitization system to the analog measuring device, so the dipoles and the ADC, that will also cause reflections and things on the signal, and that is frequency dependent. Typically, because everything is enclosed in temperature stabilized environment, And the digitization system is so close to the analog system, we don't have a lot of rippling effects on the frequency response of the system, but they are there and they have to be calibrated for. These we refer to as the bandpass effects, and these are frequency variable, but usually time stable, so temporally stable. This is again an amplitude and phase effect. So at this point we have multiple effects, and so let's look at them in the chain. So what we refer to this measurement of equations, this measuring equation is the radio interferometric measurement equation. It basically just gives us a way to describe all the various different sources of propagation error on the signal that we're trying to measure. Now, let's start closest to the measured signal. So the E of I, so where I is just antenna, some antenna, that measured signal has a bunch of induced terms. So going from left to right here, we're going from the measured signal to the purest form of the signal. So let's have a look at the various different effects. So as we visually illustrated before, we have a cable delay term, right? So this can be given by a phasor Jones matrix. Then we can have a gain term, which is temporary variable, right? So phases can change due to both the systemics and things like the ionosphere and so forth, right? Then we have this bandpass term, and as I said, the engineers go to great lengths to actually make this a stable effect, so we can actually decouple the frequency effect the system has on the signal from the temporal effect it has on the signal. So we can solve for these terms disjointly. So we have this B Jones term here, which is the bandpass, and that, as I said, is primarily driven by our orthomotor transducer, so the measuring device. So then we also have the cross-hand delay. So remember, we have this physical delay between the X dipole and the Y dipole, and the bit of delay between the two different signal paths. So that introduces circular polarization. We have non-orthogonality, so leakages, as the D Jones term here. We have the antenna response, which is a direction-dependent response. Doesn't only apply like to all portions of the sky equally. It's unlike a electronic gain term. It has this dependence on the L and M cosines of our interferometer. It's also frequency variable. So the far field response for a highly directional system such as Meerkat will shrink as a function of increasing frequency. Then we have the sky rotation because we have our system is mounted on an alt-azimuth mount, right? So this is the parallactic angle Jones or P Jones term. Then we have another delay term, which is the geometric delay, which we know perfectly, and that's just a decomposition of the sky cosine, so the difference between the source position and with respect to our fringe stopping center onto the antenna baseline vector. So just remember that the baseline itself is always measured as a function of wavelength. So there's the wavelength, there's a frequency component coming in here. All right, and so this essentially, as we'll see a bit later in our imaging lecture, this describes a Fourier transform, just as a heads up, of all sources to the sky related to the spatial coherence measurements that we're making with the interferometer. So, but this term is known exactly. All right. So now that we know what effects there is on the signal and how to model them, let's relate our correlated visibilities back to parameters that we might be more familiar with, so the Stokes parameters. So there are 4 parameters here: the total intensity, I, the horizontal vertical polarization, Q, the 45 or negative 45 polarization mode, Stokes U, and the circular polarization mode, Stokes V. Now, in the IAU convention, Stokes Q points towards the north in our local antenna frame. That gives us the vertical polarization mode. Towards the east, we have negative Q, so that's the 2 different states, states of polarization. Between the vertical and the horizontal, we have a U component. So at the 45-degree separation, we have perfectly Stokes U aligned polarized signal. And then, of course, we have the circular polarization, which is just, as we mentioned before, just a delay between the signal propagating through the horizontal and vertical components on a plane as it propagates through that plane. Now, the unpolarized source, just to recap, will have no Q, U, and V components, but it will have equal chances of going through the X or the Y measuring device. So it has equal power on those two bands. In this convention, the right circular polarized signal is defined as the Y component lagging, so phase difference behind the X component. So the equations there in the bottom right converts between the correlated signal between the X and Y hands respectively back into I. We use the convention in software where we store essentially half of that power on each of these correlations. So there's a factor of 2 coming into play here. But that's just by software convention. All right. So how do we calibrate for these various different effects? Well, one of the simplest algorithms to minimize the error between what we are measuring with a model of what we should be measuring affected by gain terms, which we're solving for, is just the ordinary least squares Gauss-Newton method. Now, you're seeing here that we are trying to minimize the error function, which is this epsilon, indicated as epsilon over here. So we are taking the minimum between a data vector and a model vector as it's affected by gains. So you can see that the model vector is parameterized by this A vector, which is just a series of gain terms. You can think of it. All right. So this describes the error function. And if we go through the algorithm step by step, if you want to take the minimum of that, you have the Jacobian on the left-hand side there. The Jacobian is just a matrix of the first order derivatives between the model term relative to the parameter vector. So this can be written essentially as analytically for a model vector of length m and the parameter vector of length n. So for instance, we'll have 64 different gain terms for each of the various different antennas as such. So in this matrix. So to continue on then, if we take a first order Taylor expansion, here we are doing like gradient descent to minimize this error function, right? Where we have essentially an update rule defined as we defined over there. The gain vectors, the gain vector is then updated repetitively from an initial starting guess, which can just be a randomly initialized vector. And then if the rank of the data vector and the model parameterized vector is the same, then we just have Newton's method, if you recall back to your university calculus. And for a radio interferometer, we can slightly modify this just to more familiar notation here. Again, we can bin all the measurements into frequency and time variable bins, which depends on the signal to noise that we have, that we need to be able to solve. So a longer bin will give you higher signal to noise to solve for effects, but may negate highly temporal variable effects. So there's always a play-off here, but we typically bin our solutions into these two-dimensional bins. So we have our visibilities described as the data point between antennas P and Q, so and this as a vector. Then the gain terms here we can describe as these 2x2 matrices, where we solve for each of the real and imaginary components separately in this case. And that's so those are our gain terms, and we have an input model. Typically, to start off with, we look at a very simple field where we have a bright source right at the center of the field. So we know perfectly what the visibility should be. They should be constant because it's the middle of the center of the field. And we can just describe this by a single point source model. Now, so we solve for all of these gain terms, 64 of these 2x2 matrices through a series of steps. So let's look at how this is implemented in software, just coming back to a practical implementation. So firstly, we vectorize the real and imaginary components, so of this data vector. Remember, so I said we solve for them separately, right? The model vector is then generated in similar fashion, so we split the real and imaginary part. This is typical approach that's followed in calibration software such as CASA. We define our error function, as I said, between the data vector and what we expect, so our parameterized model vector. We randomly initialize our guesses for the gain terms, right? And then we run a routine such as the least squares routine that's implemented in SciPy. And then we repeat all of that for each time slot or time or frequency slot, depending on how you bend up your data. So now that we know how to describe the various different places of propagation error on our signal, and we know how to calibrate for those various different terms, we can move on to a practical strategy of observing calibrators and target fields and solving for these various different propagation errors. So this process of transfer calibration solves for, primarily in the first order at least, the receiver or the orthomotor transducer filtering and transmission line effects. So remember that we have a frequency-based effect that's primarily stemming from our transmission line between the measuring device and our analog to digital converter. The system may also be temporarily variable, so there may be cable delays that is changing slowly with time, or ionospheric conditions that is introducing a phase difference as function of time. And all of those terms is solved for in this process. So in the second order, we have the non-orthogonality of the feeds. So that's the leakage terms. These terms are, as we mentioned, only about percent level errors. And then, as we said, the thermal and mechanical tension on the transmission lines may introduce slight variations in the cable delay, in the cable delays between various different antennas. So in practice, the engineers who designed these radio interferometers does a good job in making sure that the frequency response of each of these receiver systems are temporarily stable, right? That means it doesn't change with time, so we can, in practice, decouple those effects from the temporal variations, which to the first order just attenuates the signal and maybe delay it in phase slightly. The importance here, as we mentioned in the least squares method, is placed on primarily signal to noise, right? So here signal to noise is given, the desired signal to noise is given as this measurement in decibels, dB, in this equation. And the rest of the equation describes how long you need to observe for to be able to derive a calibration solution for a particular choice of channelization interval in this two-dimensional time frequency binning that you're using for your gain solutions. Now, in this equation, S describes the flux density of a field. Typically, we choose a very simple field to calibrate on in the first order. So to perform what we call bandpass and gain calibration, we choose simplest possible field, which is just a point source at the phase tracking center. So that S term there describes the total flux in the field. We have a finite bandwidth that we bin this solution into. So this delta nu term is just that bin. So if we're solving per channel, it will just be the channel resolution of the instrument. Right? As I said, the desired solution variance here is described in dB. So that's that gives our desired signal to noise. And then the system equivalent flux density describes the temperature of predominantly the electronics of the system. The low noise amplification stages within the receiver chain primarily drives the noise in the system. So that dominates this, what is known as the system equivalent flux density. All right, so how do we observe a target field, taking into account that our system is not perfect? So we'll switch between calibrator sources in this case. So in order to calibrate the frequency response where our channelization is very narrow, we need a really bright source, right? So this is the primary calibrator. And in the plot there on the left, you see amplitude versus time. The visibility is indicated by the scatter in black is the primary calibrator. That's the brightest of our calibrators. Then we have a secondary calibrator, which may be slightly closer to the target field, so that we capture the relatively global variation in the ionospheric phases as a function of time, because our primary calibrator, it may be very far away. These sources, these bright point-like sources, are few and far between. So we need the secondary calibrator in order to calibrate primarily the phase of a temperature stabilized system such as Meerkat as a function of time. And on the right hand side there you can see that we have our target field, which is deep 2 in this particular instance. We have a calibrator field in red in the 0252 there. We have a primary calibrator 0408 slightly further away. Just to indicate why we need the secondary calibrator in this case. So the typical observation strategy then goes as follows. The bandpass calibrator, which we observe primarily just to calibrate the frequency response, is observed few and far between. Right? Remember that we state that the frequency response of the system should not change in a well-designed system. Then we have the gain calibrator dispersed in between observations of our target field. So a typical observation will maybe start off with a bandpass and observe it every few hours, and then have short 2 to 5 minute scans on a gain calibrator interspersed with a target observation, which may have a length of 20 to 30 minutes. Okay, so remember that we said the highest signal to noise necessary is that needed for the bandpass, where we take that solution that we just derived, we interpolate it onto our secondary calibrator, right, to correct for the frequency structure of the instrument, and then we solve for the temporal variations induced on the signal. And with those two solutions combined, we can interpolate it onto our target field, which is indicated there in orange. And that those solutions in the first order are just delays, constant offsets in frequency varying with time, so the gains, and then the bandpass, which is just a frequency variable effect. All right, well, remember that this is primarily driven by signal to noise. However, often we have RFI and high temporal RFI and so forth in there, so that we may need to actually observe the calibrators for longer in order to wash out most of the RFI in an average. The systematics may be temporarily stable, but things like the ionosphere may have a slightly higher variance, in which case the effects that we're trying to solve for changes within the bin that we're solving for. So there's always this interplay between achieving enough SNR to derive solutions that's not time variable versus the time variant effects that we're trying to actually capture within the solutions. Then, as I said, the calibrator might be very far away from the target field, so this all drives the necessity to observe calibrators within our observation and the lengths that we observe them for. All right, so going into how we actually solve for these various gain terms. So if we assume that the leakages are really almost negligible, so the percent level leakages, then we can focus primarily first on our diagonal calibration problem. Now let's linearize the rhyme that we described earlier. Then what we see is on the diagonal term we have a set of gains for the two different antennas, I and J here, and that affects our measurement of primarily the Stokes I component for an unpolarized source. So in this case, we won't have any contribution from Q or leakages from U. So these G components really describe multiple sources of calibration errors. So both delays, K, gains, G, and the bandpass in this case. So a source with really a well-known level of flux is necessary to actually compute these terms. Remember that our interferometer is essentially uncalibrated by the point where we receive raw visibilities from our system. So we need to assign a flux scale to our measurements, and we do this with a very well-known, very bright source. All right. The key to calibration really is not just to look at the quantities that we solve for, but to look at the corrected data. So what happens if we apply the calibration solutions that we've solved for? Well, we should see that if we observe a very simple point-like field, that all the visibilities are relatively constant with some noise. There will always be noise on the system, but they should be scattered around some level of amplitude, and in this case it's in Jansky's, and the phase variance in that therefore should be close to zero, right? Modulo some noise. Now, in the uncalibrated visibilities, you can see that the spread is huge. We do not expect this for a point-like source. However, if we have calibrated our system successfully, then we will see a much more compact phase ball, as we refer to it colloquially. So the key is to visualize, diagnose. So things like RFI will obviously stand out in this plot. Recalibrate if necessary, and continue this process until you're happy that your transfer calibration has done the correct thing before you actually continue on to interpolating it over to subsequent gain calibrator or target fields. Now, the on-axis leakages, right at the pointing center of the antenna, post this correcting for these KGB G terms, can then be described as follows. So now we've taken out the G term here by performing calibration, and for linear and circular basis we get the following linear equations. So what we need to solve for now is two effects primarily. So firstly, we need to solve for leakages, and secondly, we also need to solve for the delay difference that's introduced by the system on the signal that gives us circular polarization. So that delay difference will take a signal that is inherently linearly polarized and turn it into a signal that is circularly polarized, apparently. So we need to undo that. So let's see how to do that. Now, what we typically do is we focus on an unpolarized source to calibrate the diagonal of our Jones matrix. Then we calibrate it both in frequency and in time, with a source that has essentially no linear or circular polarization, so a completely unpolarized source. Now, then we switch to calibrating the delay difference between these two different feeds, so the X and Y feeds, or the right-handed and left-handed circular polarization, and we solve for the cross-hand delay, what's colloquially referred to. Right? For this, we actually need enough signal to noise on the cross-hand term, so the correlations between the X-hand and the Y-hand of antennas P and Q respectively. So for this, we really do need a source that is intrinsically highly linearly polarized and unresolved. Okay, that source should be well modeled, so we should know its linear polarization angle and its spectrum and so forth. These solutions then is, as we stated before, is known as the X-Jones terms. All right. If we solve for those sources of error, these phase terms E of rho and E minus of rho in the X, Y, and YX correlations fall away. So we're left with typically just a bit of leakage. So on the Meerkat system, the cross-hand phases is typically orders of magnitude larger than leakages. So leakages really is a tertiary effect for us. And we solve for it then lastly using an unpolarized source again. So now whatever is left on the off diagonals should just be a form of leakage from total intensity into our measurement of 45 or negative 45 degree polarization. For a perfectly calibrated system, what we expect is to see on a linearly polarized source is just conjugate visibilities on the cross-hand products, right? And this is exactly what we see. So we should see that the linear polarization angle is stable with time if we take into account the parallactic angle, which we know exactly. So it's stable in time, and you have this conjugate measurement of Stokes U plus or minus some noise indicated in red and black in this diagram below. So this is typically what you should see for your, if you're observing a polarized, well-known polarized field. And again, the key here is really to visualize and inspect your calibration solutions after you've calibrated. If you have any further questions, please feel free to contact me on my email address. It's biego@sk.ac.za. Thank you so much for your time.